Okay, so Sho Yaida is currently a research scientist at Meta AI. He studied black holes while earning his PhD in physics at Stanford University. He then shifted to working on the glass problem during postdoctoral work at MIT and Duke. Recently, he's been working on the theory of deep learning and has done really beautiful work investigating finite width neural networks. With Dan Roberts and Boris Hanen, he is co-author of a recent book, The Principles of Deep Learning Theory, an effective theory approach to understanding deep neural networks, published by Cambridge University Press. We are really delighted to have him present a few highlights, as I understand, from his research today. Thank you, Sho, and please take it away.
Oh, thank you for the nice introduction. So I'm going to be talking about effective theory of deep neural network. And as someone said, basically this talk is based on the work that I did with Dan Roberts, who is both at MIT and Salesforce, and Boris Hanen, who is at the Princeton University. And we put this work out on arXiv last June. But if you want to hold the physical copy, then it should come out soon from Cambridge University Press, hopefully in May. Okay, so I'm going to be really, so since I cannot talk everything about the book because it's like, it has thousands of equations and 400 pages. So I'm going to be very like high level. And so here we go. So I'm going to first, so since I understand this audience is like in the intersection of physics and machine learning, I would like to first begin the talk by philosophizing like what we aim to do, well, at least I personally hope to do in this field. And then I'm going to talk about the overview of like what more technical part of this talk would be. And then I'm going to talk about neural network first at infinite width and then finite width. Okay. And since, well, please ask questions. I know that it's hard on a virtual setup, but I would really appreciate you asking questions. Okay, so physics of machine learning. So deep learning is very powerful. And if you've been to many deep learning talk or any deep learning talk, you see like some impressive chart, impressive picture, and impressive text. So I will let you fill in your mind like what they are. But basically impressive chart describing like how the deep learning is taking off, like all the accuracy is going up, like for the past decade, starting from 2012. And so there's some chart like that. And also like some pictures where like a non-trivial picture that models can classify or even generate from using the generated models. And similarly for the text, you can now like translate many languages back and forth pretty reliably. And also you can even like start to generate human-like sentences. Okay, so that's pretty impressive, but I'm not going to bore you with all these details. And for us, like I guess coming from physics, like what makes this kind of, well, the utility of this deep learning should make you also be interested in like how it's working and so on. So, and there are like two motivations for going into this field. One is more historical, so I'm gonna first say that. So back in the day, we had steam engine, which was kind of changing the way the civilization worked. And some people like Kernel and other people got interested in how it works, and out came the thermodynamics and statistical mechanics, which led to many wonderful things. So that's nice. And one hope is that history repeats. So we have some deep learning. And it's actually already leading to wonderful things, but we can maybe fill in the blank in the middle where we can have more, we can have some kind of interesting theoretical framework that appears by studying deep learning on its own, and then hopefully improve things later or as we speak. Okay, so another motivation or another angle you can take is more pragmatic one. So we can ask like what physicists can bring into the field that, well, like we can ask ourselves like what we are good at, and then we can try to utilize that. Okay, so like physicists have been, so this is just a list of my own, like you can add or subtract anything. But from my point of view, I guess physicists are good at dynamics. So like since beginning from Newton's, like we have been studying the dynamics of things for centuries. So we have many techniques to analyze them or way to think about it. And if you do glass physics, then like you like there's so many talk about landscape geometry. So maybe you can use that insight. And also like fast sampling algorithm, like we have a bunch of Monte Carlo sampling thing, fast algorithm. So maybe you can think about coming up with a better optimizer of some sort. And as we teach undergraduate, or if we teach well, then we should be able, we are pretty good at taking some limits where you can do computation and then back off that limit to do the perturbation theory around it. Okay. And also we are good at symmetry, maybe, like using symmetry to simplify the problem. And finally, I think most importantly, we are kind of good at modeling the real phenomena. Like we don't idealize too much, or hopefully, we don't idealize too much, and then we take the we try to cook up a model which can still encapsulate the real essence of the phenomena. Okay, so that's on the one hand, and then on the other hand, like there are machine learning people, I don't know how to call them, like machine learners, but like better way to get, or better way to identify what the good architecture would be for the model, the program you're looking at, how to initialize the models, how to optimize the model, and also like how to sample the data efficiently from the distribution. So these are two sides of the things. So physicists are good at something, and then machine learning people want something. So the pragmatic way to look at it is just to connect the dots as much as possible. So you can do whatever you like to, and then try to connect the dots. And in this talk, what I've been doing, sort of at the high level, is that I'm going to solve dynamics in some limits, and then there's a perturbation around it, and then solve the dynamics there. And also, like during the perturbation, like we try to capture the real, some essence of the real phenomena or real deep learning models. There's heating system going on here, so like I hope there's not so much noise. Yes, it's fine. No complaints. Cool. So that was very vague philosophy, and I'm gonna go into more technical things. Okay. No questions so far. Cool. Okay, so okay, we want to understand deep learning, but to understand them, like we need to set a concrete goal, especially for a 1 hour talk. So I'm gonna first review what the machine learning is in one slide, and then try to set the goal that we are trying to answer. Okay, so in machine learning, what you do at first is to instantiate, or after specifying architecture, you try to instantiate the model. So at initialization, you have some function fnet, so initialization, which takes input x, and this is more specifically a function of two things. So one is the input x and set in it, which is the model parameters at initialization. And I'm going to give you some concrete example in the next slide. But so that you have some model parameter theta, and you draw the model parameter from some distribution that you specify. And then you train the model. So the most orthodox way to do it is the stochastic gradient descent, or some variants like stochastic gradient descent and Adam. But in essence, you specify the loss function L that you want to minimize, which characterizes how well the model is doing right now. And you take a derivative with respect to model parameter. You take a step in a direction of steepest descent, where eta is we usually call learning rate, which specifies like how much big a step you take. Okay. And then you keep training model by iterating this process, and then you get the trained model at the end. And now, which takes an input X, but now using the theta model parameter after training. So, and in particular, you try to take an X that you didn't see during the training and see how well it does make a good prediction on the unseen data. Okay, so the goal is to understand this last function, not the initial function, but the function after the training. Or at least like that's what I want to do today. And more specifically, since you have distribution of initialization model parameter, like each time you draw the initial model parameter, you train, you get the different model at the end. So you basically create this distribution of trained model at the end of the training. And by studying statistics of this PF trained, like for example, if you take a mean, then you can see that what the typical prediction model would make on a given input. And by studying the variance, you see like how much fluctuation you would have from instantiation to instantiation, or from paper to paper, if they use different seed. And you can also even study higher statistics if you want. So this is the goal. And then this is like one difference I want to highlight from, I guess, mathematician to physicists, between mathematician and physicists, that the mathematicians tend to look at the worst case scenario, whereas we tend to look at the more typical case. And that's basically sort of what we are doing. So, okay, so I see one hand. Shailesh.
Can I ask a quick question? The distribution of F trained, will it depend on model architecture and parameters as well as the data that it has been trained on as well?
Sorry, I didn't hear the first part. Can you say that again? Sorry.
I was asking about the distribution that you have in the boxed equation, P of F trained. Will its parameters depend both on the model architecture that you started with, as well as the data that it has been trained on, or is there some independence?
Yeah. So there are, So I'm going to come to that soon, but yes, of course, yes. Even on initialization here, the distribution of initial function depends on the architecture and how you specify the model, how you specify this initial distribution of model parameter. And then after training, like it does also depend on the data set, and also in principle on the algorithm you use. Because like whether you use GD, SGD, or Adam, it should give you some dependence. Although we will see that at infinite width limit, that's going to be gone, which actually we want to recover, but I'm skipping ahead myself. But
thanks.
Thank you for asking a question. Cool. Okay, so that's the goal, but then that's kind of abstract even for me. So let me give you some concrete example, which is a multi-layer neural network, but more specifically the multi-layer perception, just as a pedagogical example. Okay, so the network function usually takes input X as a vector, like say pixel images, and then you pass on a bunch of layers, and then at the end you get the output. Okay, more specifically, let me, so the multi-layer perception is defined by this recursion equation. So you take input X, then you multiply by W, which is weight, and then you add something B, which is called bias, and then what you get is what's called first layer pre-activation, so these black dots in the figure. And then you pass on this white blob, which is called activation function. So this is a nonlinear function you choose beforehand, before training. The historical first choice is perceptron, but then people have done sigmoid, tanh, sine, linear, ReLU, soft plus, swish, and GeLU these days. I guess ReLU is the most popular one, but people now use GeLU for transformers, and historically tanh was also important, I think, and sometimes people do sine and so on. Okay, but anyway, so this is the nonlinear function that you specify, and it acts on each pre-activation you had from the previous layer. And from there, the same game again, multiply by weights, at the bias, you get some pre-activation here, you activate weight multiplication, bias addition, and so on and so forth. You repeat this like capital L times, and what you get is the output function F, which is, I made it to be scalar here, but then it can be vector, or it usually is vector. Okay. So now this function f depends on these b and w's, and these are the model parameters I mentioned in the previous slide. So in this case, the theta, the model parameter, would be a very gigantic concatenated vector of biases and weights from all the layers, from first layer to the L layer. Okay. And one more thing that I talked about is the initialization distribution, which that would be specifying how the bias and weights are distributed before the training. And the typical choice is the IID from mean zero Gaussian, or sometimes people do mean zero uniform distribution. But they are characterized by the variance. So this is the variance for biases, and this chronicle data is just a fancy way to say that it's IID distributed. So each component is drawn from the different Gaussian distribution with the same variance. And similarly for weights, W. And here, I think the note is that it's divided by n L minus 1. So this is number of neurons in the previous layer. So if you're looking at the weights here, the number of neurons here is 5. So you normalize by 5. So in this talk, since I don't go into detail, this just looks like a normalization constant. But it turned out that when you try to do the careful calculation to take infinite width limit or really wide limit, then this is the most normal normalization. But the motivation is to just keep the pre-activation order 1 for all the neurons in general. Okay. Cool. So you don't have to remember all these details because I'm not going to talk about the details. But two things I want you to remember is these two numbers, n and l. So n depicts the width of hidden layers. So in this figure, it would be 5, but in practice, it'd be like hundreds and thousands or even more. And then depth is basically roughly how many times you repeat the same operations. So say 10 or 20 or more, depending on how much deep network you have. And now the number model parameter is roughly n squared times L. So n squared because you're connecting the n and n neurons in adjacent layer, and you have L of them. So that's and in a very modern state-of-the-art models, it could scale up to billion number of model parameters. So that's rough numbers to have in your mind. Okay. So again, so now that we have a concrete model in our mind, we can parse this slide better. Okay, so you instantiate the model. So initialization here, you have bias and weights drawn from IID Gaussian distribution in each layer. You train them by gradient descent. Now you ask the distribution of this ensemble of neural network that are trained. You ask about mean, variance, and so on and so forth. Cool. Okay, so we want to understand like this distribution of function after training. Okay, but then like when you try to do so, then there are 3 problems that we encounter in general, which can solve, but then let me illustrate what they are. So to illustrate them schematically, let me expand the trained function, f trained, around the initialization function. Okay, like expanding around initialization. So first, this is just for freshman year, or even, anyway, freshman calculus. So you have f init, and then you have first derivative of function at initialization, and you have difference between trained model parameter and initial model parameter. You have second order derivative, and so on and so forth. So what are the problems? So problem 1, in general, there are too many terms in this series. So if there's no reason for this series to have so in general, you could think that these questions are all order, then you have to keep track of everything, which would be pretty hard to do in general. And 2, even though we have complete control over this distribution over the initialization, because that's what you specify in your code, in this, on the right-hand side, you have this first derivative term, and second derivative terms and so on, and also initial function function itself. And you want to understand all of these to understand the distribution of this object on the left-hand side. So you have to actually have some way to map from the model parameter distribution to the distribution, the cross distribution over the model parameter functions, first derivative and second derivative, and actually infinite series of object. So even going from the left to right here is pretty hard in general. And even more, lastly, you have what you want to understand, or we want to understand here is the distribution over the trained function. So you have to actually go from the second object to the last object. And to do so, you have to solve the complicated dynamics. And to do so more specifically, you have to have, in some sense, you have to have this set of train as a function of set of initialization object, like set of init, f init, and so on. And also, I alluded to in answer to one question, like it should depend also on algorithm you use and data you use. So this is what you need to solve to get from the second to the last. One question, Anindita?
Hi, thank you. My question is, what are all the constraints you are considering on the training and the loss function to be able to write down the trained network distribution as a Taylor series around the initialized network distribution?
So we're going to assume that we are dealing with a neural network on the architecture side. And so that's one. And I'm going to describe what the limits are. In terms of algorithm, we can solve gradient descent and also for sure. And then SGD you can in principle do as well. At least like at infinite width, it's pretty easy, like actually at least the same minima. But in finite width, then there are some part that start to depend on the algorithm, and it's easier to see for gradient descent, but then it'd be nice to generalize the stochastic gradient descent. And I guess one thing I'm curious about these days is Adam case, like how it looks like even at infinite width limit. But yeah, so we are not putting any unrealistic constraints, and like we can study anything. But what I'm going to present is about the gradient descent mostly today.
Okay, thank you so much.
Yeah, of course, thank you.
Could I ask a tiny follow-up question?
Okay, sure.
Thanks. It seems like it would assume that the function is analytical in the parameters in order to have such an expansion. But if you have a ReLU nonlinearity, isn't it that would hold? Yeah,
that's a great question. So first of all, like it does work for smooth functions, but as you point out, the ReLU is a tricky case, and it turns out that if you do this expansion, then the infinite width limit is fine. So I'm a little bit skipping ahead, but I think you're fine with that. But when you talk about the finite width correction to the dynamics, and then you see a little bit subtlety, like in how NTK change. Maybe do these words make sense to you, or? Okay. So NTK change, and then like usually for smooth function, it's like 1/n, but then it's like 1/√n for ReLU, and then you probably need different tricks for ReLU. So either you could say that for the kinky, the function that has this continuity in derivative, you have to have some different way to attack it. But also these days, people are actually replacing ReLU by JReLU in vision transformer. So you could say that maybe you can follow the suit of the practitioners and then work with the smooth function, because actually when you do the experiment, like you don't see much difference between ReLU and JReLU. So I see. But yeah, academically there are interesting questions there, like how you come these like 1/√n correction come about for these kinky functions.
Thank you.
Yeah, but rest assured that the things is mostly fine here. Okay, great. So just to rewind because there were questions. So we're trying to understand this train function distribution. But in general, you have a bunch of model parameters, and you think that in general, you have a bunch of things, too much things, and you may have two different perspectives depending on your personality. So one is to despair. So if you take, especially if you take a microscopic perspective, focusing on individual components of all the weights and biases, then you might say that the more model parameter you have as you do, then the phenomenon becomes more complex. So we are doomed and we can do nothing about it, and then we just forget about it and do nothing. Or you can take a more macroscopic or optimistic view, drawing some lesson from statistical physics that you can focus on the averages rather than individuals. So in this case, maybe the more model parameter you have, the phenomenon becomes simpler. And so maybe we can do this task of solving or getting some control over train functions after training. Okay. Basically, the main message is twofold for this talk. One is that there's drastic simplification that happens when you take an infinite width limit, or when there are infinitely many neurons in hidden layers. And this is just a manifestation of law of large numbers. And for physicists, it means just that you have a Gaussian free theory at infinite width when n is infinite, n is number of hidden layer, neurons in a hidden layer. But well, we hope not to stop there, because you cannot really instantiate the infinite width network in your computer unless you have infinite money, but that's going to collapse the universe, so you shouldn't do that. So you don't have, this is not real model. You're kind of sacrificing the essence of deep learning in a sense. So we should systematically go beyond this idealized limit by backing off this infinite width limit. And AKA, like this is just a application, the technique we know and love, which is perturbational theory. And this will be like a weakly interacting theory, if that word makes sense to you, when the width is much larger than depth. So basically you can do something like 5-4 theory, you can do the perturbation theory and calculate things, which is fun. Okay, so more specifically, these words shouldn't make sense to you now, but then should hopefully make sense later at the end of this talk. That, well, the statistics initialization and after training becomes sparse, and dynamics can be truncated, so you can solve things quantitatively. Sven?
Yeah, it's just a question. We can also postpone it to later if you feel like it. Regarding the comment about that it has to be a free theory at n equals to infinity. So in what sense is this generated? Because is this guaranteed to be actually true? I mean, there could still be some interactions that can play a role. And
right, so it depends on the way you take a limit. But if you take a limit in a way that I specified, then it's going to be Gaussian theory. For example, you could think that maybe you put the seed for Gaussianity by having the Gaussian distribution for the weights and biases, but it turned out that that's going to be gone. Like the higher statistics of that distribution doesn't matter. And I also said, well, let me go back here. But if I take the limit in a way that you keep this CW to be order 1, whereas this hidden layer to be n, then normalize this way, it's going to be Gaussian. And there's similar thing about the learning rate. And I guess to be more complete, there are recent new prescription given by Greg Yang et al. At Microsoft, which lists the different distribution after training. And that theory is interacting, I think, as far as I know.
Yeah.
But I'm not going to take that limit today.
Okay.
Yeah, I'm going to follow the thing that people traditionally have been doing, and then I will try to describe that rather than prescribing the new thing. My good friend put it. Cool. Okay. So this is where we are heading. Cool. Okay. Neural network. Any other questions? I think Sven's hand is still up, but I suppose that's gone. Okay, cool. Sorry. Neural network at infinite width, so we got to begin somewhere. So as I said, I'm going to be very schematic, and I'm going to try to suppress every indices, and that is hopefully meant to be pedagogical for this talk. But then there are some weirdness that happens. But then this is just to give you the high-level picture. Mostly fine. Okay, and I'm not going to derive anything, but I'm going to just tell you the result. Okay, so training dynamics at infinite width. So at first, you have this gradient descent of model parameters. But what we want to understand is how the function behaves. So you want to keep track of function, evolution of function. And to do so, you can actually expand in this change of the model parameter. So you have, what you have is the function at t+1, at the iteration t+1, you have the function before, and then you have change in the function in first order in this expansion. And then you, in principle, would have higher order terms. But it turns out that when you take this higher order correction is of order 1/n, so you can actually suppress them in this infinite width limit. And here, this first order question H is called neural tangent kernel, and it roughly looks like a derivative function over model parameter square. Okay. Let me know if you hear noise, because, well, anyway. H, so neural tangent kernel NTK H, where for physicists, this is like a Hamiltonian, so that's why I denote it by H. It just governs the evolution of function at this order. And you might think that, oh, I wrote the NTK T, so it might depend on time, iteration, but it turns out that the changing NTK is also 1/n suppressed. So n is number of neurons in hidden layer. And if you take infinite width limit, then it's going to go away. So basically in this limit, it turns out after some long sum dance that NTK doesn't evolve. So NTK would be fixed or frozen at the initial value. And the function evolution simplifies further because you can take this to be constant. Okay. So now you take this evolution of function, and let's take some concrete example, even though actually the answer doesn't depend much on the detailed form of the loss function you take. And there's some algorithm independence, which is nice for theorists, but then weird for practitioners in this limit. Anyways, you take this mean square loss or square error loss or square error loss, f minus y squared. So y is the label that you have, for the target, a few inputs that you have in a training data set, and you try to minimize the difference of your function to that correct answer. Okay, if you plug that into the previous slide, taking derivative with respect to f, then you get f minus y. So you get this linear homogeneous equation. That's just a way of saying that it's a piece of cake for us to solve. So you get the exponentially decaying function, and you can get the closed form, but then at each step in time, in iteration. But in particular, you get the training after the infinite step. Well, it exponentially converges. So even if you take enough steps, then it converges quickly to this solution in infinite width limit. So f train, the training after function after training, is described by initial function minus this NTK at initialization and inverse of that, and the f minus y. Here is the one weirdness that happens because of my pedagogical throwing away of all the indices, but you think that this is 1, but it's actually not 1. Because H is actually constrained to the training data. H inverse is constrained to the training set, but please don't. Oh, okay, Sven.
Yeah, so on that footnote, this is a certain degree as a question. I mean, I see, it's very nice to work with mean squared error. but I want to push a little bit because like if we think about more complicated loss functions, in particular ones where you know, you have actual, you know, different labels effectively, like for you know, if we want to classify something, etc. Then I don't see necessarily that, you know, this, you know, they seem to be, to me, structurally different in the sense that
what do you mean by different labels?
So like you classify
different why?
Yeah, so that you know, you have a a cat, a dog, etc. Right? So it's not something some kind of universal label that you kind of.
Oh, I didn't mean that. So like that dependence is still here in Y here.
But still, I think so. So mean squared error in any case is still a special function in the sense that.
Yeah, I know.
It decouples things. So
yeah. So maybe I missed.
So the question is essentially like when you say it doesn't matter. So there must be some assumptions in the sense of, okay, it won't matter because I don't buy the argument for general loss function.
Yes, well, so it doesn't matter in a sense of if you take an infinite risk limit, it doesn't matter. So it depends only on the label you use and like how, like as long as those functions should be minimized at Y when the function is Y, and then that Y would go into this expression, but then other details of the loss doesn't matter.
You can think about loss functions where you have interactions effectively, right? So,
well, so what I'm saying is, so actually, like your objection is correct that it shouldn't be the case, but in an infinite risk limit, it turns out to be the case. So that's like all the more reason to back off this limit, right? Because it's killing that information that's usually matter in practice, but then in an infinite risk limit, you don't see that. So there's something weird going on.
Mm-hmm.
So, but that's just the math, and I actually, this is actually a nice, thing that you can cure by backing off this limit. Shailesh, I guess I shouldn't try to pronounce the name. I cannot.
Yes, that's sorry. Just another quick question. What is the fate of the loss function at the end of training? Does it? Can you drive it down to 0, or does
yeah. So in an infinite risk limit, essentially you have like you can fit all the data, with the exception of when your function is not too constrained. Like if you take deep linear network, for example, you can approximate only linear functions. So if the label is cannot be linearly labeled, fit by linear function, that's one subtle caveat. But in general, yes, because you have, infinite number of model parameters, you might expect that you can fit them all.
Thanks.
Yeah. Anindita? Sorry. To back off, like we are always working on in this more over-parameterized regime where you can fit everything. Okay. Yeah, sorry.
No problem. Just a quick follow-up question on Sven's question. So if I consider the simplest loss function, absolute value of f minus y, is the construction still going to hold, or is the non-differentiability at f equals y going to cause some problems?
I have never thought about that. It's possible because you get only sign. Yeah, well, probably, yeah. I mean, like, I guess I wouldn't do f-1 absolute value in practice, but that's a fair point. I don't know what happens. But you can actually, you can try to solve on your own time if you feel like, and let me know the answer.
Sure, thank you.
Yeah. You get the sign here, so I guess. Well, let me not do this on the fly, but that's a
sure,
nice maybe graduate or undergraduate student program exercise.
Thanks.
Cool. Thank you. And okay. Cool. Okay, so digest of this whole thing is that you get the expression of trend function in terms of initial, the object at initialization, like function and NDK. So basically, we have established going from the second thing to the last thing you wanted to understand. So the only thing left to do is to fill in this first part of the math. And since like actually the only function and NTK seems to appear in this, like I just suppress all the other statistics, because that's the only thing that matters for our goal. Okay, so actually this has been done nicely by including people in this audience. There's someone. So Gaussian, it turned out that the distribution of function, this f at initialization, is just given by Gaussian distribution. So this was actually realized for one hidden layer network by Rutherford Neal in 1996, but then which has been kind of ignored, I think. But then Google people at Google Brain, nice Jaifeng Lee and Yasaman Bari and other people, actually extended this to deep neural network when the hidden layer number of neurons in the hidden layer goes to the infinite width limit. And then there was also a concurrent paper by Matthew et al. At ICLR 2018. So if you like math, you should look at the latter one. If you like physics, then you should look at this former one. Is the flavor of these papers. But at the end of the day, you basically get this distribution of Gaussian, and Gaussian distribution is basically specified the covariance, and this is K, and this K, which is called sometimes Gaussian process kernel, or just kernel. And this is some calculable matrix, and actually there's a recursion equation that specifies this K. And further, like you can ask about what happens for NTK, and the distribution is even simpler. The simpler distribution that's simpler than Gaussian is the direct delta function. So you get direct delta H in it minus theta, where theta is calculable matrix. And this is just a fancy way of saying that each time you draw the model parameters, you basically get the same number or same matrix again and again for NTK at infinite width limit. So it's just picking a singular value. Well, not singular value, but yeah, theta, and theta here is called, usually this is actually the way people denote NTK usually, theta, capital theta, and this is again some calculable matrix that's recursively specified. Okay, so you establish this first map, and then you basically solve everything in this limit. So the distribution of trained network is Gaussian distribution, with mean given by this frozen NTK, inverse NTK, acting on label Y, and variance involving K and theta you can write down. So this is like as simple as you can imagine, but it's as kind of discussion with Sven alluded to, is missing some parts, key part of deep learning. So since we talked about this, let me talk about second element first. So there seems to be no algorithm dependence except a few things like what label they are and so on. So that's weird because in practice you see all the dependence on like which algorithm you use and such, and you're not seeing that here, or like batch size and such. Okay, and also there's no representation learning. And for the physicist who is just entering deep learning, the representation learning just means that the ability of a model to learn useful representation from data. And that is like, at least at the folklore level, what the deep learning is buying you. And there's none of that in this limit. So this seems to be too simple to describe real deep neural networks. So this is, nonetheless, it's a useful starting point. But if you want to understand deep learning in its completeness, then it's not the end of the story. So we will go beyond that. Okay, so I'm going to be very brief, and then I can just take question on the chat that's accumulating, I guess. Okay, cool. And your network at finite width, so I'm going to just tell you the result pretty quickly. So what happens is that the okay, so initial distribution was Gaussian in an infinite width limit, but then if you back off, then you have some nearly Gaussian distribution, which is to say that it's a Gaussian thing with the quadratic term and so on in exponential, but the quotient in front of that is small, so you can do the perturbation expansion around it, around the Gaussian. And this is described in detail in section 4, chapter 4 of the book. And also you can furthermore solve the dynamics, and it's going to be weakly nonlinear learning dynamics, which is to say that you can actually use the time-dependent perturbation theory. And once you understand that, you can just crank the wheel or whatever people say, and then like just do the. It's a little bit messy, but then you can do it, and you can actually get the closed form solution after the training in terms of initial object initialization, and also like you can see how the algorithm dependence come into the solution, so on and so forth, and you get the nearly Gaussian distribution of train function, which is close to Gaussian, but then there are small corrections, which is nonetheless important. So this seems a bit more complex than what you had in infinite limit, but it's still tractable if you put your mind to it. And more importantly, you start to get the effect of representation learning, and to be more to be more concrete, like you get the changing NTK. NTK used to not move, but the NTK is moving, which is kind of saying that the features are moving. And also now you start to see the dependence on algorithm, which is what happens in practice. So it's getting closer to the real phenomena, which is what we want to do as a physicist. So this is complex, a bit more complex, but tractable, but then complex enough to capture rich phenomenology of real deep neural network. And you see in particular the effect of depth and representation learning, the ability of model to learn the useful representation from data is getting enhanced by the depths. So it's nice. So, and one thing to emphasize that even though you might think that if this depth over width is small, which is actually the case in practice, usually, you might think that it's a small effect. But then as you know from physics that having interaction or not is giving you a very qualitatively different picture for you. So it's so same thing here, even though it's a small correction quantitatively, you're now getting different effect visible. And I'm not going to go into this, but then what you do is that you expand to the higher order term, and you realize there's two things you have to keep track of at 1/n, and then everything else is 1/n squared. And to Jamie's question, I think this is for smooth function, and then there are some subtlety here for the ReLU, but ignore that. This part is fine. And then you solve this equation, and you get the trend function in terms of initial object, but it's pretty despicable and horrible. So let me not show that because you get attacked on Twitter. Okay, so you get this initial distribution to the initial object, and so it basically establishes the map from second to the last, and the same thing again. You try to do the first, and I'm not going to have any time to do that. But one thing I want to emphasize for this audience, which I guess have physicists, are that actually like in doing this, like to calculate this statistics involve going from layer to layer and passing this. You first figure out the distribution of this object at first layer, second layer, third, and so on. So this picture of RG flow actually emerged in going from integrating out the model parameter from layer to layer and then passing on to the higher layer statistics. And once you establish that flow, then you can study, there's actually notion of critical ID and about which hyperparameter, there's critical hyperparameter for the initialization distribution, that, and also universality across some class of activation function, and all that fun thing as a physicist, but I'm not gonna say that today. That's another talk that I might have already given. Okay, so summary is that in an infinite limit, you get very simple picture, which is pretty nice, useful starting point. But you realize that after some calculation, that there's no representation learning, no algorithm dependence. So maybe you should back off. In addition to the fact that it's not the real thing that you can instantiate on your computer, although you can do the kernel thing. Okay, so you back off, and then when the depth hidden width is much larger than depth, the thing description theoretical description or effective theory becomes a little bit more complex but tractable. And there are representation learning and algorithm dependence. So you can start to study this expression and see what's happening. And if you take, even though I didn't say too much, like if you take the different limit where the depth goes much larger than width, then it's going to be too complex and chaotic. But it also turns out that in practice, this is not the regime people can train the network usually. So there's this emerging picture where on the axis you have depth over width, and you have infinite width limit here, which is not deep in terms of like representation learning and so on. And you crank it up. There's effectively deep regime where the actual practical operates, and also operates. And then like if you take this ratio to be too large, then there's overly deep regime. And theoretically what happens is that there's too much instantiation to instantiation fluctuation. So I think that's why it doesn't train well. There's residual thing to actually push this scale further, but then I'm not gonna say anything about that. And okay, so the main message, just I repeat, is a simplification. There's simplification when there's infinite many neurons, infinite layer, you get the Gaussian theory, you can know and love, but then it's not real, you step back, perturbation theory, weakly interacting theory. And one more thing to say is that the reason why I said it's sparse is that because when you take a infinite width limit, you had only this function and NTK, which is the composite of this, and then you add finite width, but in 1/n level, you had only 3 things. So it's even though there are like really large number of model parameters, you only have to keep track of a few objects. So it's a very sparse description, and also dynamics was truncated to linear order or cubic order. That's all. And there seems to be 7 questions on the chat, so let me end here. And 2 hands, I guess.
Thank you, Sho. I think there are a lot of questions. Maybe we can go some of the raised hands. Eva?
Yeah.
And then...
Oh, Eva. Okay. Hi.
Hey, Sho. Sorry, I could ask you this in real life, but
yeah, right. You could have asked one, 2 days ago.
Yeah, sorry. Yeah, other people should dominate this, but thanks for the great talk. I'm a little confused when you say algorithm independence at large width. I mean, but yet you also have the question about, say, how Atom is going to work, which is an open question.
Right. Yeah. I shouldn't. Yeah. Let's talk about that in a real life.
Okay.
Yeah, but yeah, I think you know what I stand on that.
No, but I mean, here you're stressing something that I want to make sure I understand what it is, because you're saying no algorithm dependent.
Yeah, so it doesn't depend on the form of the loss. It doesn't depend on whether you do SGD or not SGD, as long as linear rate decays, and so that it converges. It doesn't depend on the batch size. So
I see. So there's some independences, but some possible dependencies.
Yeah, but like when you switch to something like Atom, like I just Dan and I had some chats on the messenger, and then we disagreed. So let me, since we don't, let me not say that in public. But
yeah, no problem. Okay.
Yeah, but Adam, I think it's an interesting question, especially because it's started to feel like it's erasing something about the initialization information and so on.
Yeah, I mean, anything that isotropizes things in parameter space could go in that direction.
So maybe different form of kernel, or in which case, like, you still get the kernel thing, so the quoted conclusion stays, but the form of the kernel may be different.
Okay.
I think that would be my conjecture.
Thanks. Can I ask one more thing about this a little bit more big picture? So you have this great summary of how the goal is to get this distribution on the trained results, right?
Mm-hmm.
And then you have this wonderful way of doing it by going to perturbation theory and having control and all that. At the end, you were saying, in more general cases, it's chaotic and it's difficult. But what I wonder is, there are situations where, in a very chaotic situation, if you have certain properties like energy conservation, Liouville's theorem, you do also get a prediction for the distribution. You get, it boils down to the measure on the phase space. And
actually, let me interject that for deep linear network, you can actually start calculate many things about this regime, and you can look at like as we do in chapter 3, like at least for the initialization distribution, and then maybe it's true for even for the after the training. So yeah, could be something interesting there. But then, sorry for interjection. Please go on with your question.
No, it was just a sort of more of a comment that there are situations where it is very complex, and yet there are formulas for how the distribution should end up.
Yeah,
and that comes up in some optimization methods, for example. But
yeah,
anyway, thanks again for the
yeah, of course, yeah, and to the extent it matters, maybe I'll start with deep linear network and study what happens. Yeah, at least academically, that's interesting. Yeah. Okay, I guess then Sven and then the chat.
Okay. Yeah, hi. Yeah, thanks for this nice talk. So I have a, okay, this is also one is in the chat is about, you can look at the equations that you get for the update and see the dependencies. That's clear. But I'm on this slide, I'm slightly confused. So I'd like to, hear a little bit more on your perspective about the n equals to your perspective on the n equals to infinity case, because I kind of, the last 2 points about no representation learning and no algorithm dependence, I kind of disagree with, because there's a certain dependence clearly on, how large the learning rate was, on what I'm learning. I mean, things about gradient explosions, etc. So
sorry. So infinite limit, there's actually kind of binary question. The learning rate must be smaller than the inverse of the eigenvalue of the NTKs, but otherwise it converts the same thing. So the dependence on the learning rate goes away in an infinite limit.
Okay, good. So, but then that's okay. So, okay, one can take always these limits, but like and see what that is. I wouldn't say necessarily that n equals to infinity is so strict, but the question I actually have is more on no representation learning, because when we do the empirical NTK at large, at relatively large n. So when we really approximate that story. So,
but the fact that you're using
no. I'm just taking the linearized version. I'm just talking about the linearized equations, and just just truncate everything at the linearized level, which that n equals to infinity limit corresponds to pretty well. Then I'm still learning something. I'm still learning a non-trivial function. I'm still evolving from initialization to a non-trivial function. And so in what sense, in what sense is this a, like, can you call it a non-representation learning? Because this is some representation. It's not the representation necessarily that we know in deep networks, but we're learning some representation.
Right. So when I say no representation learning, I mean kernel is not changing. That's one precise definition. And you're learning the function, right? The function is given by kernel inverse. And that is something. And if you call the last output of the function to be representation, then you're learning something. But then it's the feature you're using from the whole network is not changing in this limit. That's all what I'm saying.
Okay, so but I think still that limit, if you're just truncating at that linearized level, you're learning something non-trivial. And this is
you're learning the function, but then you're by truncating, your indicator is not changing. So the kernel is not changing, and that's what I mean.
Yes.
Yeah.
But and so just to be clear, so in whatever solution you have of the function that you're getting out, it will depend to a certain degree on the labels. So there is a somehow a dependence on the loss function in that formula. Yeah, good. So that was the,
of course, because like it's kernel inverse y. Yeah. guess the number of hands increased, but I'll let someone decide which one.
We could do Christian. I think the chat is more a discussion, so it's
Okay, cool. Okay, I shouldn't worry about too much. Okay,
ignore,
cool.
and I want to squeeze in. So, Christian, please go.
Thanks. I'll try to be quick. So I know for RNNs, there's like a discrete transition between a chaotic regime and a regime where you have stable fixed points.
So, RNN, you said?
Yes, for RNN. And then you want to do your computation kind of the edge of this chaotic regime, where the memory capacity starts to increase.
So you mean like, do you mean in terms of like hyperparameter space? Is that what you mean?
So this is done for RNNs with randomly chosen recurrent weights, and then you're just training the readout weights, and then you're changing the parameters of the distribution of these randomly chosen RNN weights, and then you have some like chaotic regimes where the RNN just does chaotic stuff, and then it's not very useful, and you have a stable regime. Yeah. But then if you want to use this as a reservoir for computing, then you want to be kind of at the edge of that.
Yeah. Okay. So two comments. So like one, actually, I realized that the chaotic here is different thing than that chaos. So that shouldn't be confused. This just means that the higher order statistics matter, and the chaos you mentioned exists even in infinite limit, I guess, and about the exponential growth of the pre-activation and gradients backward. So yeah. Actually, that's what I meant by this criticality. And this is, there are beautiful set of papers by Benpo, Raghu, Joshua, Sam, and all the people at Google. Should I list everyone? So yeah, you want to be there. That is actually, yeah, one of the things that comes out of this study, and you can generalize to all the activation function, or when you have residual connections and stuff like that. Yeah, so the basic lesson is that there's on the one side of that critical point, then you have this exponential growth of things, and on the other hand, on the other side, you have exponential decay of things. But you want to keep everything order one in general, because that's why you are trying to, like, function that you're trying to learn is also at order one. So you want to be there, and also backward, like you want to keep the gradient to be order one, because you don't want to go a lot farther or exponentially large step or exponentially small step. So yeah.
Is the way to characterize whether my neural network is close to that critical point?
Yeah. Well, you can just take a statistics of, or even calculate analytically.
Yeah, some kind of characterization of time and more.
Yeah. So one.
Okay. Chaotic regime.
So characterization. So two things you should, a few things you can keep track of. One is just the norm of the pre-activation layer, and you see how they move from layer to layer. Is it exponentially growing or exponentially decaying? So that's one thing to keep track of. And since you have two hyperparameters, you should also specify. And either you can look at the two separate input close by and see how they deviate from each other, or they crash into each other, or you can just in PyTorch, you can just compute the gradient and then compute the sum, squared and sum, and that would be NTK. Is it now like, exponentially growing as you go backward or not? So that's, yeah, two things you can calculate. And then usually that's enough to specify where you are in this hyperparameter plane.
Okay, thanks.
And okay, so I'm not going to talk about chats, and you have to raise hand to ask question, I guess, or Jim.
Hi, Sho. Nice talk. It was cool to hear you distill this in this way for an hour-long talk, because I know you can also lecture for 10 hours on it or whatever. So if you can go to your last slide real quick, I have a pretty simple question. So the summary, yeah. So sorry, the one before that, the n equals infinity. Yeah. So you're making the point that as you move from top to bottom, things get sort of more interesting. I'm curious to the extent non-Gaussianity is the central thing there, as opposed to just finite n. So in particular, in the standard assumptions, there's a central limit theorem that's getting you Gaussianity at initialization. And one way to say that is there's you're summing an infinite number of random variables. But at infinite n, you can actually also get non-Gaussianity by breaking statistical independence of the neurons. And I was wondering if you guys have tried to carry out an analysis like this, but in this different way of breaking Gaussianity.
So one thing, actually, okay. So one thing I said, and I think this is not your question, is that you can change the distribution at each thing, but then you're asking, then like, we still get the Gaussianity, but then you're saying the statistical dependence between neurons. So like, yeah, I mean, so, okay. One example I can think of on the fly is a convolutional network where you basically have this dependence, right? Wait time, and you do still get the Gaussianity there. Because you end up like, so like the dependence between the weights in the different acting on different neuron is not enough to create the non-Gaussianity.
Yes, it's not always sufficient, but the claim is that sometimes it is.
If you can construct one, yeah, but I don't know the construction. But then I'm not trying to prove Noble theorem, and the Noble theorem always get unproven. So
I guess all I'm doing is what physicists always do, which is we consider some theorem that we like, and then we violate some of the assumptions, and we see what happens. And you guys did that by violating infinite n. And I'm saying that you can also violate the CLT by violating statistical independence.
Right. Yeah. I mean, so okay. Well, we didn't violate. We stepped back from that because
maybe not violate. You moved away from the assumption.
Right. And well, I don't know. So like that's an interesting question, and I again, like what I want to do is to describe what people are doing. So, but if you calculate but you shouldn't disguise the academic curiosity. So if you calculate something there, see something interesting, then you can like experiment. And the nice thing about being in this field is that you can have some session and just do the experiment. So you can go back to this old age of doing both theory and experiments, which is nice. But yeah.
Yeah, very good point. Yeah, people are not doing infinite n cases where you don't take IID stuff. They're doing finite n cases where you do. Finite case IID, and you still already get this neuron talking to each other effect already there. So since I have finite time, I would just focus on things that I can. I feel like, but. But collectively we have more time. So the non-Gaussianity is correlated with finite n crucially. Is your sense that the non-Gaussianity is absolutely crucial in getting this representation learning, or is it more of a finite n effect?
So I think it's crucial that the dynamics become nonlinear. I think so. The kernel needs to change. Non-Gaussianity of the statistics itself is not, I think. You can, so we have this simplified version of representation mining called quadratic model. So it's a distilled version of the real phenomena. The real phenomena is actually a cubic model. And there, the essential thing is that the NTK moves because of this higher order term in non-dynamics. So once you have there, then you can actually set these statistics of like features and meta feature to be Gaussian, and still you get the non-representation learning. So I would say,
I appreciate the point. The second you get the higher order Taylor expansion, however you get it
in dynamics,
in dynamics, then that's the crucial thing. That's going to correlate with non-Gaussianity, and maybe you can get it in this other case. Right. Thank you. Yep. Nice talk.
Of course. Oh, thank you. Sven, are you still? or maybe go to Anindita.
Sure, thank you. Mine is a kind of a naive follow-up quick question to Jim's question. So in the finite bit case, suppose you are starting with an initialized neural network distribution where you are not assuming the parameters to be IIDs. That is, you have a correlated parameter distribution, and then you also have the non-Gaussian effect. So then how is the overall description of the trained network distribution going to change with the two different effects of non-Gaussianities in picture? Suppose we are staying close to Gaussian distributions for the parameter distributions.
Sorry, so you're introducing non-IIDness in a way that Jim said, but
Close to
also
Gaussian.
close, but they're not Gaussian.
Yeah.
And you're stepping away to finite width. Is that?
Yeah, right. So like there are two different axes of
Oh.
having non-Gaussianities.
Oh, so like for the example I just gave on the fly for convolution network, this phenomenology should be the same. Just because if you kill one of the effects by going to the infinite with limit, then wait time is not enough to give you non-Gaussianity, even if you correlate the weights. But if there were a case where like statistical dependence of weights, even infinite with survive, then I guess you can, well, hopefully you can do the perturbation theory in two parameter half. Like one is 1 over n, whatever, say epsilon that introduce about this non-Gaussian correlation between the neurons or weights. So you can do double expansion like that, I guess, would be my guess.
I think my question is that in case of training, will the two independent parameters, which you call epsilon and n, will they become correlated and give us a complicated parameter? Like, can you actually do two independent parameter perturbation theory in case of training with those two different axes of non-Gaussianities?
I guess I'm not parsing your, sorry, if I'm not parsing your question correctly.
Sorry. My point is during training, will the two parameters for non-Gaussianities will still remain independent of each other, or will they become very complicated in a way that you can't actually write down the network distribution as a Taylor expansion?
I mean, so weights get correlated, and then also neurons get correlated, but then actually correlation exists even at initialization at finite n.
Right. Right.
And these are enhanced, like, because like this fluctuation, so this correlation between the neurons, which is weak, but like this correlation get employed by, well, if your inductive bias is correct and nice for the data that you're working with, then this nice features correlation get enhanced and the adversarial one get enhanced, or I hope. But you can calculate these things, but that is not the, if that is what all you want to do, then I think that's doable. But if you're asking a more deeper question about whether this is useful or not, then I need to think harder about that. So sorry if I'm not answering your question, but then maybe we can take it offline.
Maybe, in the interest of time, maybe Sven next. And there's one more question from the chat.
Yeah. So I'm kind of taking liberty as this is like a kind of casual chat after the program or something that, I'm not violating my time limit.
If anybody needs to leave, I think they can. So there's one question from Ben in the chat. Can you use the finite width effective field theory to compute the exponents of neural scaling laws for NLPs or transformers trained with SGD?
You should ask Dan. But I don't know how much to, like, you can, you shouldn't, I don't know whether 1 over n is important for this question in particular. Like there are already non-trivial things going on at infinite with limit. And people are working on it. But that's not what I'm doing right now. So let me not say too much about.
Sven, you had a question?
Oh, yeah. I mean, I was going to say that there's interesting paper by Kernel et al. And you guys et al. And so there are things going on already at infinite with limit is a safe thing to say. And you can then ask about how the finite receive effect comes in and correct the picture. And is it now important for scaling or not, and so on. So yeah, there's that.
Yeah, so you maybe answered this, but just for clarity, when you have weight sharing, so if you think about CNNs, you can think of them as like weight sharing. Does this add effectively another parameter to the story in the sense that you, for the expansion, or how would you account for it?
So
basically the distribution is not IAD, right? So you can blow up that story.
So what you do is that you expand in one of a channel. So like K by K thing and channel, and then still like K by K times infinite number of signal comes in, so the lower large number still holds.
So you have three parameters, N, L, and C, essentially. Or kernel size.
Okay, yeah, yeah. And so the term use of terminology kernel would be confusing here, but then the kernel that appears in the distribution should depend on the K that specifies the kernel size of the convolution.
Yeah.
So architecture in the device is called in the kernel, but otherwise the qualitative picture should be similar.
Okay, maybe I can squeeze in my one question. They didn't have a raise your hand button. If I understand, I think you're probably assuming like the learning rate is an order 1 quantity in your analysis.
Right. Yeah. So one thing I suppressed here is where did I? Oh yeah, here. Let's say here in NDK, I should have actually written like lambda mu nu here, which is like 1/n for weights, because otherwise this NDK would blow up. So the learning rate for the weights should be suppressed by 1/n, and the biases, the learning rate for biases are order 1, and the eta in front is kept to be order 1, such, and then you're just inserting one more thing here, like parameter-wise learning rate that is to ensure that the NDK is order 1. And I think that's the most crucial difference between what we do and what Greg et al. Does. He assumes the different way of scaling learning rate per parameter, especially at the beginning and end, I think. And that result in something different.
And so like the learning rate, does it get corrected with like depth over width corrections, or you can still working in the same range of learning rates that you would have at
great. So okay. So once you take this 1/n scaling, then now you ask about the depth dependence. As you know, like NTK at criticality grows linearly for ReLU, for example. So you now, like even if you're infinite with limit, like if too deep, then you should rescale eta the learning rate by 1/L, the depths. So, but yeah, we do say this in the book, but it's buried in later chapters. But anyway, yeah. So the way we operate is that they first take care of all the scaling with width. Now you solve things that you're interested in, and now you realize the depth dependence, and you try to adjust for the learning rate. But that's a weaker dependence. Parallel. Actually, both of them are parallel. But yeah, actually, like some experiment you see that the learning rate should be rescaled by depths and so on, or inversely. Yeah, so that's consistent.
Great, cool, thank you. I think we will end there, and these are really pressing questions. Thank you for the wonderful talk show, and yeah, we really appreciate it, and it was great, lots of stimulating discussion. So
thank you. Right. Have a good week.
Yeah.